Welcome to my channel Phi Concepts CHM. This video is the first part of electrical properties of metals. We are going to see first the introduction, then physical properties of metals, and the Drude's classical free electron theory of metals. Introduction. Motion of charged elementary particles in solids gives rise to resistivity. That is, the materials offer resistance to passage of electric currents. Hence, resistance is developed when charged particles collide with other particles in the material. In metals, electrons collide with the individual charged ions. Physical properties of metals. Metals obey Ohm's law. That is, current in the steady state is proportional to the electric field strength. Metals have high electrical and thermal conductivity. At low temperatures, the resistivity ρ is proportional to T raised to 5. At high temperatures, ρ is proportional to temperature. For many metals, ρ is proportional to 1 by P. The resistivity of an impure specimen is given as ρ is equal to ρ0 plus ρ of T. This is the Matheson's rule, where ρ0 is a constant for impure specimen. ρ of T is the temperature dependent resistivity of pure specimen. Near absolute zero, the resistivity for some materials falls to zero. Such materials exhibit superconductivity. Conductivity varies in the presence of magnetic field. This effect is called as magnetoresistance. The ratio of thermal conductivity to the electrical conductivity is proportional to the absolute temperature. This law is called as the Weidmann-Franz law. Free electron theory of metals. In 1900, Drude gave the free electron theory of metals to explain theoretically electrical conduction in metals. He treated the free electrons in the metals as ideal gas of free particles, which in thermal equilibrium obey the Maxwell-Boltzmann statistics. In thermal equilibrium, there are on an average as many electrons wandering through a given cross-section of the conductor in one direction as there are in opposite direction. Therefore, the net current is equal to zero. In non-equilibrium state, resulting from the application of electric field or thermal gradient, electrons are subjected to instantaneous collisions. During each collision, electron loses the energy acquired from the field and makes a fresh start. Also, direction and magnitude of velocity is changed. leading to a zigzag motion of electrons. Energy is lost by the electrons in the process, which increases the thermal energy of the ions. These collisions serve to return the distribution to the equilibrium situation. Using kinetic theory of gases, an electron has mean free path lambda, mean collision time tau, and root mean square velocity c bar. We will find the expression for c bar. In the absence of external electric field, pressure exerted by the electron gas at temperature T degree Kelvin according to classical theory for unit volume of metal, P is given as 1 by 3 rho c bar square. Substituting rho as m into n, this becomes 1 by 3 mn c bar square. Equation 1, where m is the mass of the electron, n is the number of free electrons in unit volume, rho is the density of electron gas. For molar volume of metal, we will substitute in place of n, Na upon Vm. So this becomes 1 by 3 m into Na upon Vm into c bar square. This is equation number 2, where Na is the Avogadro's number and Vm is the molar volume. Therefore, PVm is equal to 1 by 3 m into Na c bar square. From the ideal gas equation, PVm is equal to RT. Substituting this here, we get equation number 3. Rearranging equation number 3, we get mc bar square is equal to 3RT upon Na. Again, R by Na is K, which is a Boltzmann constant. Substituting this, you get mc bar square is equal to 3kT, equation number 4, where R is the universal gas constant. Kinetic energy is given as half mc bar square. Substituting in this from equation number 4, we write 3 by 2 kT. So we get c bar square, which is 3 kT by m. Taking the square root, we get c bar, which is square root of 3 kT by m. Equation number 5. Now we will calculate the conductivity of metal on the basis of classical theory. Electric field applied to a metal exerts a force given as F is equal to E into E. Equation number 6. The force acting on each electron produces an acceleration. So substituting F is equal to ma, this becomes ma is equal to E into E. From this you get acceleration A is equal to EE by m. Equation number 7. Consider an electron that has just collided with the iron core. The collision will momentarily destroy the tendency to drift, and the electron will have random direction after the collision. Also, at its next collision, the velocity of the electron again changes, and on an average the velocity will be given as k into tau. Tau is the mean time between the collisions. Tau is given as lambda by c bar, equation number 8. The average velocity a tau, which is also called as the drift speed, is given as v suffix d is equal to a tau. Substituting a, we get E by m into tau, equation number 9. Also substituting equation number 8, tau is equal to lambda by c bar. Here we get Vd is equal to E by m into lambda by c bar, equation number 10. Drift speed is the steady average velocity imposed by the field and proportional to it. Current density J is the charge crossing unit area in unit time. We write current density J is equal to Ne into V suffix D. Substituting from equation number 9 for Vd, we get Ne into E tau by m. So this becomes Ne square E tau by m. This is equation number 11. From Ohm's law, conductivity can be given as sigma is equal to J by E. We can substitute current density from equation 11. So E will get cancelled out. So this will be Ne square tau by m, equation 12. Also substituting tau is equal to lambda by c bar, we get Ne square by m into lambda by c bar. So sigma is equal to Ne by m into lambda by c bar. In this we will substitute c bar, which is root of 3 kt by m. So that becomes m upon 3 kt the whole raised to half. This root m and here also you will have root m will get cancelled out. So we get sigma is equal to Ne square lambda upon square root of 3 mkt. Equation number 13. Now we will find the resistivity of the metal, which is rho, which is the reciprocal of sigma 1 by sigma. So take the reciprocal of equation number 13. So that will be square root of 3 mkt by Ne square lambda. Equation number 14. From this equation 14, we understand that rho is directly proportional to T raised to half. Equation number 15. Equations 13 and 14 are classical equations for electrical conductivity and electrical resistivity. Therefore, from classical theory, rho is directly proportional to T raised to half. But experimentally, rho is directly proportional to T, which leads to the failure of classical theory. Also, mean free path lambda is taken to be independent of temperature, but it is not. However, Ohm's law can be derived. Thank you for watching my video.